26 light-years away, a telescope has captured something that defies reason: water vapor on a world where the very ground could melt metal. This planet, known as GJ486b, races around its star so quickly that a full year lasts just 36 hours. Surface temperatures soar to nearly 800 degrees Fahrenheit. By all logic, no atmosphere should survive here. And yet, the James Webb Space Telescope has detected the unmistakable signal of water hidden in the infrared light streaming past this alien world. But here's where the mystery deepens. That water may not belong to the planet at all. It could be lurking instead in cooler regions of the star itself, a celestial illusion that would upend what looked like the first atmosphere ever discovered on a rocky exoplanet. Scientists are divided, the debate fierce and the implications enormous. So, if you love unraveling the universe's strangest enigmas, hit like, subscribe, and join us, because we're about to plunge into one of the most controversial discoveries in modern exoplanet science. The journey begins. The signal first appeared on screens at the Space Telescope Science Institute, like a faint whisper from another world. Scientists leaned closer, eyes fixed on the data streaming back from the James Webb Space Telescope. They had turned humanity's most powerful eye toward a rocky planet, 26 light-years away, expecting silence. Instead, they found water vapor. The news rippled through the astronomical community. Water vapor wasn't unusual on a gas giant like Jupiter, but this was different. This was a rocky super-Earth. If the signal was real, it would be the first atmosphere ever detected on a rocky planet beyond our solar system. The telescope had been watching a world named GJ486b, catching it as it crossed in front of its star. Each transit lasted only an hour, but in those fleeting minutes, the starlight filtered through whatever clung to the planet's upper edge. That light carried fingerprints, chemical signatures, and hidden among them was the unmistakable mark of water molecules, absorbing very specific wavelengths of infrared light. 3 independent teams, using 3 different methods, reached the same conclusion: water vapor. But then came the twist. Perhaps the water wasn't on the planet at all. GJ486b orbits a red dwarf star, a type notorious for dark, cooler patches called star spots, similar to the sunspots on our own star. These regions are cold enough for water vapor to survive, which meant the signature might not belong to the planet, but to the star itself. Computer models confirmed the maddening dilemma. A planet with a water-rich atmosphere produced one signal. A star covered in vapor-filled spots produced another. The two were nearly identical. As Sarah Moran of the University of Arizona explained, "We see a signal, and it's almost certainly due to water, but we can't yet tell if it belongs to the planet or the star." For decades, scientists have hunted atmospheres around rocky exoplanets. They found them on gas giants, on hot Jupiters scorched by their stars, but never on a world like this. Never on a planet built of rock like Earth, even if its surface burns like hell. The stakes could not be higher. If GJ486b truly holds onto an atmosphere, it would prove that rocky worlds can cling to their air even under the harshest conditions. And if a planet this close to its star, blasted by heat and radiation, can survive with an atmosphere, then what of the countless cooler, calmer planets scattered across habitable zones in our galaxy? But first, we need to understand the kind of world we are dealing with. Imagine Earth, squeezed until it weighs 3 times as much, yet grows only 30% larger. That is GJ486b. Its gravity would crush you, your weight tripled, each step like carrying 2 more versions of yourself on your back. Astronomers call such worlds super-Earths, bigger than our home, smaller than the icy giants Neptune and Uranus. GJ486b was first confirmed in 2021, when its orbit betrayed it through the faint dimming of its star. It sits in the constellation Virgo, a sprawl of stars that emerges in the northern skies of spring. And there, orbiting in silence, it keeps its secrets, waiting for us to learn whether the water belongs to the planet or to the star that scorches it. But GJ486b is nothing like the gentle maiden its constellation suggests. This world is a furnace. Its surface blazes at nearly 800 degrees Fahrenheit, hot enough to melt lead, to turn zinc into liquid, to make rock itself begin to flow. The numbers tell the story. Its density reveals a body of iron and stone, much like Earth at its core, but that's where the resemblance ends. Astronomers know its size from the fraction of starlight it blocks during each transit. They know its mass from the subtle gravitational tug it exerts on its star. Put those two together and you unlock density, and density unlocks composition. Gas giants swollen with hydrogen and helium are airy and light. Rocky worlds are heavy, compact, forged from minerals and metals packed tightly together. By every measure, GJ486b is rock and metal, nothing less. It circles its star once every 36 hours, 1 year shorter than a weekend on Earth. The planet hurtles around its sun at blistering speed, held in a tight gravitational embrace. That nearness is both curse and gift. The curse, unrelenting radiation, heat beyond imagining. The gift, proximity makes the planet easier to study. Each transit blocking a larger fraction of starlight, giving us a stronger signal than worlds farther away could ever offer. But what truly defines this planet is not its orbit, nor its heat, but its rhythm. GJ486b doesn't spin like Earth. It is almost certainly tidally locked, forever showing one face to its star. On one side, a hemisphere of eternal day, scorched under constant fire. On the other, a hemisphere of endless night, frozen in perpetual shadow. And between them lies the terminator, the thin border where day and night meet. If this world has an atmosphere, the terminator would be a place of unending chaos. Heat would roar across the divide, whipped into supersonic winds, clawing to balance the extremes of light and dark. But if no air exists, then silence reigns, the day side burning, the night side frozen, with nothing to bridge the two. And everything hinges on that single question. Does this scorched world truly hold on to its atmosphere, or is the signal nothing more than a mirage? So why does this planet cling so close to its star? At first, 26 light-years might sound impossibly distant, but in the language of the cosmos, it is astonishingly near. 1 light-year is about 6 trillion miles. The distance light travels in a single year at 186,000 miles per second. Multiply that by 26, and you have the distance to GJ486b. Yet against the scale of the Milky Way, it's practically next door. Our galaxy stretches 100,000 light-years across. If the Milky Way were the continental United States, Earth would sit somewhere near Kansas City. GJ486b would be less than 2 blocks away. By comparison, the Andromeda Galaxy would be another country entirely, and the observable universe would dwarf the planet Earth millions upon millions of times. We live in a neighborhood, and GJ486b is one of our nearest neighbors. Its star, GJ486, is a red dwarf or M dwarf, the most common type of star in the universe. Nearly 70% of all stars belong to this class. They are small, cool, and faint compared to our Sun. GJ486 holds only about 30% of the Sun's mass and glows with less than 2% of its brightness. From our distance, it appears as nothing more than a faint red dot, invisible to the naked eye. Because red dwarfs shine so dimly, any planet seeking warmth must orbit extremely close. The so-called habitable zone, where liquid water could exist, hugs the star tightly. But GJ486b orbits even closer still, far inside that safe band. That's why its surface is scorched beyond recognition. Yet the same closeness that makes the planet inhospitable makes it invaluable for science. Each time it crosses its star, a greater fraction of starlight filters through whatever atmosphere it might possess. The nearer the planet, the stronger the signal. And when you're chasing something as delicate as the whisper of an atmosphere on a rocky world, every advantage counts. Distance matters, brightness matters, planet size matters, and in this case, GJ486b checks every box, close enough, large enough, and bright enough to give scientists a fighting chance to uncover its secrets. GJ486b is just the right size to block a measurable amount of starlight, and its rapid, regular transits give astronomers multiple chances to study it. But that closeness comes at a terrible cost. Red dwarfs may glow cooler and dimmer than our Sun, but they are far more violent. They are monsters disguised as embers. These stars unleash storms of radiation, sudden flares that can increase their brightness tenfold, even 100-fold, in a matter of minutes. Imagine our own Sun flaring 100 times brighter in an instant. Earth's atmosphere would be ripped away, oceans would boil, life would end. This is daily reality for planets that orbit too close to red dwarfs. The danger is greatest in their youth. During their first billion years, red dwarfs erupt with constant tantrums. X-rays and ultraviolet light hammering nearby worlds for millennia. Atmospheres are shredded molecule by molecule. Ultraviolet light tears water apart into hydrogen and oxygen. Hydrogen, the lightest gas, escapes into space. Oxygen either drifts away or fuses with rock. In both cases, the result is the same. The air vanishes. GJ486 is billions of years old now, calmer than in its infancy, but the scars of its past eruptions remain. For eons, it has bombarded its planets with deadly radiation, which is why finding water vapor near GJ486b is so shocking. By all logic, this world should be bare, stripped clean, a silent rock orbiting a fading ember, and yet Webb saw the whisper of water, somehow, somewhere. But red dwarfs hide another twist. They live unimaginably long lives. Our sun will shine for about 10 billion years. Red dwarfs can burn for 10 trillion, 1,000 times longer. The universe itself is only 14 billion years old. Not a single red dwarf has yet died of old age. They are all still young or middle-aged, destined to outlast every star like our sun. This longevity changes everything. If rocky planets around red dwarfs can cling to their atmospheres, or rebuild them, they have trillions of years for life to take root, trillions of years for evolution, trillions of years for civilizations to rise. That's why scientists care so deeply about GJ486b, not because of this one world alone, but because it stands for billions of others across the galaxy. And to understand what it means to orbit so close to such a star, consider its speed. A year on GJ486b lasts just 36 hours. While we on Earth sleep through 2 nights, this planet completes an entire orbit. It tears around its star at 200,000 miles per hour. At that speed, you could travel from New York to Los Angeles in just 80 seconds. Its star blazes only 2 million miles away, barely 1/50th, the distance between Earth and the Sun. And this breakneck orbit creates consequences that defy the imagination of anyone standing on Earth. On GJ486b, there are no seasons, no gentle shift from summer to winter, no months, no calendar, no sense of time as we know it. If humans could somehow exist there, which they cannot, they would celebrate a birthday every 36 hours. A teenager would already be thousands of years old in Earth terms. The very concept of a year collapses into meaninglessness. From the surface, the star dominates the sky. Because of the planet's close orbit, the red dwarf would appear 15 times wider than our sun does from Earth. It would fill the heavens with a vast crimson disk, dimmer than daylight on Earth but overwhelming in its size, an ever-present ceiling pressing down from above. Astronomers can trace the orbit with precision. Each time the planet crosses its star, as seen from Earth, the starlight dips in a regular pattern, every 1.467 days, like clockwork. That consistency tells us the planet's path is stable, a gravitational dance that has likely lasted for billions of years. But here is the unsettling truth. The planet itself probably doesn't experience a 36-hour cycle at all. Like Earth's moon, it is almost certainly tidally locked. One face stares at its star forever, baking in relentless heat. The other remains hidden in eternal darkness, frozen in shadow. The day side is a place where the star never sets, hanging motionless in the sky. The night side is a black void where the star never rises. Between them lies the terminator, a narrow twilight strip where the star lingers permanently on the horizon, casting endless sunrise or sunset. Tidal locking happens when a planet orbits so close that the star's gravity pulls harder on one side than the other. Over millions of years, this tug slows rotation until it stops entirely relative to the star. The same hemisphere faces inward forever. On GJ486b, that means a day side burning at 800 degrees Fahrenheit, hot enough to melt metal, while the night side may plunge to hundreds of degrees below freezing, perhaps even approaching absolute zero if no atmosphere exists. On that side, gases like carbon dioxide would crystallize and snow down as ice. The terminator might be the only region with marginally survivable conditions, a thin strip of permanent twilight. And this is where the mystery of water vapor matters. If the planet does have an atmosphere, it would transform the entire world. Heated air on the day side would rise, cooler air on the night side would sink, and colossal winds would scream from hot to cold at supersonic speeds. Those winds would spread heat, softening the extremes of fire and ice. Astronomers can test for this by mapping the temperature across the day side. If the hottest point sits directly beneath the star, that suggests weak winds and little to no atmosphere. But if the hotspot shifts away from center, carried by high-speed currents, it would be evidence of air in motion, proof of an atmosphere. For now, the only clue is that ambiguous signal of water vapor. It could belong to the planet. It could belong to the star. No one can say for certain. But what we do know is this. Temperatures on the day side soar to 800 degrees Fahrenheit, hot enough to melt lead, hot enough to unmake the very idea of habitability. At 450 degrees Fahrenheit, paper ignites. At 621 degrees, lead melts. At 786, zinc turns to liquid. GJ486b's surface exceeds all of these thresholds. If you could somehow stand there, which you absolutely could not, your body would combust instantly. The ground beneath your feet would glow a dull red from its own heat. Any water that somehow reached the surface would vaporize before it could even form a puddle. Scientists calculated this scorching temperature using multiple methods. They measured the star's light, factored in the planet's distance, and accounted for how much energy it reflects versus absorbs. All paths led to the same conclusion. This is a world at the edge of what rock can endure. Basalt, a common volcanic rock on Earth, begins to soften around 2000 degrees Fahrenheit. GJ486b isn't quite that hot, but it exists in a range where different minerals behave in extremes. Some rocks remain hard and brittle, others soft and almost plastic. For comparison, Venus, the hottest planet in our solar system, averages about 870 degrees Fahrenheit. But Venus achieves that heat thanks to a crushing carbon dioxide atmosphere, 90 times denser than Earth's, which traps warmth and keeps the night side nearly as hot as the day. GJ486b might have no atmosphere at all. If it's truly airless, the day side would blaze at 800 degrees while the night side could plunge toward -300, a temperature swing exceeding 1000 degrees. Across the Terminator, this extreme heat poses a challenge for the water vapor mystery. If water exists in the planet's atmosphere, where did it come from? Surface water would have been long gone, boiled away billions of years ago by relentless heat and radiation. Any present water would require a continuous source. The most plausible candidate, volcanic activity. Deep below the surface, water could survive as superheated liquid or steam under immense pressure. Volcanic eruptions could vent this steam into the atmosphere, temporarily replenishing it. But there's a catch. The planet must still be geologically active. Mantle convecting, volcanoes erupting. Scientists do not yet know if GJ486b is alive inside or dead. For a super-Earth 3 times the mass of ours, retaining internal heat for billions of years is possible, but unconfirmed, and that brings us back to the central puzzle. Is the water vapor on the planet or the star? Red dwarfs have another trick that complicates matters. Like our sun, they develop dark spots where magnetic fields suppress heat. But unlike sunspots, these star spots are far cooler. While a sunspot drops from roughly 10,000 degrees to 7,000, a red dwarf surface might be 6,000, with spots as cool as 4,000 or less. That temperature difference is critical. Water molecules cannot survive at high heat. They split into hydrogen and oxygen. But in cooler regions, water can exist as vapor. Our sun is too hot for this, but a red dwarf can host water in its star spots. Spectroscopy confirms it. Water vapor exists in the atmospheres of these cool stars, concentrated in their dark patches. Here's the complication. When a planet transits its star, it may pass in front of a star spot. The light that filters through the planet's potential atmosphere also carries the water signature of the spot. The two signals merge. Any atmospheric water on the planet becomes entangled with the star spot's water, making it nearly impossible to separate with current technology. Researchers have modeled both scenarios. One placed water in the planet's atmosphere. The other model placed water in the star spots. Both scenarios, the planet's atmosphere or the star's dark patches, produced transmission spectra that matched Webb's observations almost equally well. The difference between the two only emerges at shorter wavelengths. Below the range, Webb's NIRSpec instrument observed. To resolve the mystery, scientists need new observations with a different instrument called NIRSpec, capable of probing those shorter wavelengths. If the water signal grows stronger at those wavelengths, it likely originates from the star. If it weakens or disappears, the water is probably in the planet's atmosphere. But those observations haven't been completed yet. The question remains unresolved. Red dwarf stars like GJ486 complicate matters further. They are magnetically active, covered in star spots, sometimes blanketing 10% or more of the stellar surface. With a planet the size of GJ486b transiting such a star, it is almost guaranteed to pass in front of at least one spot during the hour-long transit. This contamination is unavoidable. Every transit measurement for a planet orbiting a red dwarf carries this intrinsic ambiguity. Scientists first identified this problem back in 2018, years before the James Webb Space Telescope even launched. Researchers at the University of Arizona predicted that red dwarf star spots could mimic atmospheric signals, warning that separating planetary atmospheres from stellar contamination would become one of exoplanet science's greatest challenges. With GJ486b, that prediction proved true. The very first attempt to detect an atmosphere around a rocky planet orbiting a red dwarf ran straight into this problem. Fortunately, the telescope has tools to cut through some of this uncertainty. Light carries information. Each photon passing through a gas leaves a signature. Certain wavelengths are absorbed, others pass through, untouched. These absorption patterns create unique fingerprints for molecules. Water absorbs strongly at specific infrared wavelengths. Carbon dioxide absorbs at different ones. Methane has its own distinct signature. By spreading starlight into a spectrum and measuring which colors are missing, scientists can decode the chemical composition of distant atmospheres without ever leaving Earth. This technique, called transmission spectroscopy, is revolutionizing our understanding of exoplanets. Here's how it applies to GJ486b. The planet orbits its star every 36 hours. Once per orbit, as seen from Earth, it passes directly in front of the star. During that roughly hour-long transit, a tiny fraction of the star's light filters through the planet's outer layers. If GJ486b has an atmosphere, the light interacts with it, each molecule leaving its mark. If it is airless, the starlight merely grazes the rocky surface and continues onward, leaving no fingerprint. It is in this delicate interplay of light and matter that the mystery of water vapor hides, teasing astronomers with the possibility of an atmosphere and keeping them guessing. When starlight passes through water vapor, the molecules vibrate and rotate in response to specific infrared wavelengths. Those wavelengths are absorbed, converted into heat, while the remaining light continues toward Earth, now missing those specific colors. The James Webb Space Telescope collects that light and spreads it into a spectrum, a rainbow revealing how much light arrives at each wavelength. Where water vapor absorbs, there's a dip in the spectrum. Where nothing absorbs, the spectrum stays flat. Astronomers observed GJ486b during 2 separate transits to confirm the signal. The first transit revealed the telltale water absorption feature. The second transit showed it again. That repetition mattered. Consistency confirmed the signal was real, not a fluke, noise, or instrument error. Each transit lasted about an hour, enough time for the telescope to collect the photons needed to produce a detailed spectrum. These observations used Webb's near-infrared spectrograph, or NIR spec, operating between 0.6 and 5.3 microns, the infrared range where water vapor leaves its strongest fingerprints. For the most part, the spectrum remained flat, meaning the planet's atmosphere, if it exists, blocks roughly the same amount of light across most wavelengths. But at the shortest wavelengths, around 1 micron, a small bump appeared, precisely where water vapor absorbs. The match wasn't perfect. The error bars, representing measurement uncertainty, overlapped between the planet atmosphere model and the star spot model. The signal was there, tantalizing yet ambiguous. 3 independent research teams analyzed the data using different statistical methods. All 3 reached the same conclusion. The bump likely comes from water vapor. But all 3 also acknowledged that star spots could produce the same effect. The data simply isn't clean enough to tell the 2 apart. This is the nature of working at the edge of technology. At these limits, scientists see hints, suggestions, possibilities, not certainties. Observing twice is critical. Seeing the planet transit once is intriguing. Observing it a second time is science. When the telescope first captured GJ486b crossing its star, the water signal appeared immediately, demanding confirmation. Space observations are costly. Each hour of telescope time is precious, competed for by hundreds of teams worldwide. But the potential of detecting an atmosphere on a rocky exoplanet justified a second observation. The planet transits every 1.467 days, so the next opportunity arrived quickly. The telescope focused again. 1 hour of observation, the same instrument, the same wavelength range, the same analysis techniques. If the first observation had been a fluke, the second would have shown something different. It didn't. The water vapor signature appeared again, the same bump at short wavelengths. The signal was real. Something in the system produces it. The question remained, planet or star? Multiple observations also reduce noise. Photons arrive randomly. Detectors have imperfections. Cosmic rays can create false readings. By averaging multiple transits, random errors cancel, strengthening the true signal. This is why astronomers repeat observations, not out of mistrust, but for proper statistical rigor. The two transits were separated by months, introducing another advantage. Red dwarf stars rotate once every few weeks. If star spots were responsible, a spot could have moved between transits, altering or erasing the signal, but it didn't change. This could indicate water in the planet's atmosphere, or it could mean the star is so covered in spots that the planet always crosses at least one. Without additional data, scientists cannot decide between these possibilities. Each transit generates hundreds of gigabytes of raw data. That data flows from the telescope to the Space Telescope Science Institute in Baltimore, where it passes through calibration pipelines. These pipelines correct for instrument effects, remove known noise sources, and convert raw detector counts into calibrated spectra, ready for analysis. Once the spectra are fully calibrated, they reach the science teams, who analyze the data using sophisticated computer models. From observation to publication, the process takes months of meticulous work. But the case of GJ486b is exceptional. Studying this planet required developing entirely new techniques. No one had ever attempted to separate a planetary atmospheric signal from star spot contamination with such precision. Researchers had to build fresh computer models, simulating star spots, create advanced statistical methods for comparing model fits, and develop new ways to estimate uncertainty. In a sense, GJ486b isn't just a planet. They are pioneering the tools needed to study thousands of similar worlds in the future. The results were simultaneously promising and frustrating. Flat spectra are usually boring. That's what makes this one extraordinary. When the transmission spectrum emerged from the analysis, most wavelengths showed almost no absorption. Across much of the infrared, the planet blocked roughly the same small fraction of starlight. A flat spectrum can mean either a bare, airless planet or an atmosphere with no strong absorbers. Scientists had hoped for dramatic valleys in the spectrum, deep troughs that would clearly signal gases in the atmosphere. They didn't find them. Then came the subtle rise at short wavelengths, between roughly 1 and 2 microns. The spectrum curved upward, showing the planet blocking slightly more light at those wavelengths. The precise region where water vapor leaves its mark. The increase was small, the error bars were large, yet the feature was reproducible across both transits and matched water vapor's spectroscopic fingerprint. That tiny bump in an otherwise flat spectrum became the center of an international debate. Flat spectra are deceptive. An airless planet produces them naturally. No gases, no absorption. But a cloudy atmosphere does the same, as thick clouds block light equally across all wavelengths. And star spots add their own complexity. When the planet crosses a star spot, the star's effective temperature changes slightly. That temperature shift can mimic or obscure atmospheric features, producing a nearly flat spectrum. Disentangling these effects requires detailed modeling of both planet and star. Researchers compared the observed spectrum to two competing models. The first assumed a water-rich planetary atmosphere, simulating how light would pass through it while accounting for temperature, pressure, and clouds. The second assumed no planetary atmosphere, but water vapor in star spots, simulating the effects of star spot temperature and coverage. Both models fit the data almost equally well. The statistical difference was negligible. This near tie between competing explanations is common at the cutting edge of science. When instruments are pushed to their limits, clear answers are rare. Instead, scientists gather hints, competing interpretations, and tantalizing possibilities, all fitting within the error bars. This ambiguity is not a failure. It is the nature of exploration. The first observations of anything new are always uncertain. Clarity comes later with better instruments, longer observation time, or refined analysis techniques. What makes this flat spectrum surprising isn't just its lack of dramatic features, it's what it implies about the planet itself. Most models of hot, rocky exoplanets predict strong absorption from water, carbon dioxide, or other gases. Seeing almost nothing suggests either a very thin atmosphere, a planet with unexpected composition, or no atmosphere at all. None of these outcomes match what scientists hoped for. yet all are profoundly interesting. The three independent analysis methods tell another story. Replication is the backbone of science. Observing the same feature with multiple techniques and teams strengthens the conclusion, even when ambiguity remains. It's a delicate balance between discovery and doubt, a reminder that at the frontier of exoplanet science, certainty is rare, but possibility is endless. When three independent teams analyze the same data using different techniques and reach the same conclusion, that result gains significant credibility. That is exactly what happened with GJ486b. Three research groups took the transmission spectra from both transits and ran them through separate analysis pipelines. The first used a method called cross-correlation, which mathematically compares the observed spectrum to theoretical templates of various molecules. The second employed Bayesian analysis, a statistical approach that calculates probability distributions for different atmospheric compositions. The third applied retrieval modeling, running computer algorithms to search for the best-fitting atmospheric parameters. All three methods pointed to the presence of water vapor, not because the scientists expected it, not because they hoped for it, but because the data, rigorously analyzed, consistently revealed absorption features matching water's spectroscopic fingerprint. The odds of all three independent methods converging on the same molecule by chance are vanishingly small. Either water exists somewhere in the system, or some other effect is perfectly mimicking its signature. An unlikely but not impossible scenario. Cross-correlation works by creating spectral templates for various molecules at different temperatures and pressures. The algorithm shifts and scales each template to match the observed spectrum. A high match produces a high cross-correlation score, while a poor match scores low. For GJ486b, water vapor templates consistently generated the highest scores, while carbon dioxide, methane, ammonia, and others scored lower. The method isn't flawless. It can be influenced by noise or systematics, but it is robust when a real signal exists. Bayesian analysis takes a different approach. Rather than comparing templates, it calculates probabilities. Starting with prior assumptions about likely gases and plausible temperatures, it updates those assumptions based on the observed data. The result is a probability distribution showing which atmospheric compositions are most likely. For GJ486b, models including water vapor had higher probabilities than those without, though the error bars were large, suggestive, not definitive. Retrieval modeling is the most computationally intensive method. Millions of atmospheric simulations are generated, varying temperature, pressure, composition, and cloud properties. Each simulation produces a theoretical transmission spectrum, which is then compared to the actual observations to find the best fit. For GJ486b, the models that included water vapor matched the data best, while those without water matched poorly. Despite this consistency, caution remains. All three methods share a key limitation. They cannot distinguish whether the water resides in the planet's atmosphere or in star spots on the host star without additional observations at different wavelengths. They can tell us water exists somewhere in the system, but not exactly where. This ambiguity is why the star spot hypothesis remains plausible, even after three independent analyses point to water. Star spots themselves are far more complex than they appear. They are not just dark patches, they are windows into magnetic turbulence. Magnetic fields, generated by churning plasma in the star's interior, burst through the surface, suppressing heat flow and creating cooler, darker regions. These spots can dwarf entire planets. On the Sun, sunspots cycle roughly every 11 years as the magnetic field flips polarity. Red dwarfs like GJ486 have similar cycles, but their magnetic fields are far stronger, and their spots can cover a much larger fraction of the stellar surface, sometimes 10 to 20%. Imagine the Sun with spots that size. Earth's climate would swing wildly as huge dark patches rotated across the solar disk, and life would contend with dramatic fluctuations in sunlight. Planets orbiting red dwarfs don't have that stability. Their star's brightness can vary significantly over days or weeks. Within a star spot, temperatures on a red dwarf can drop to around 4,000 degrees F, while the surrounding surface remains near 6,000 dF, that 2,000 D. Difference creates a chemical oasis where molecules that cannot survive on the hot surface suddenly become stable. Water vapor forms, carbon monoxide, titanium oxide. These molecules accumulate in the star spots, creating distinct chemical signatures that can be detected spectroscopically. When a planet transits, it may cross these molecular-rich regions, and the resulting absorption can be mistaken for a planetary atmosphere. The challenge for studying exoplanet atmospheres is deceptively simple to state, but fiendishly complex to solve. When a planet passes in front of a star spot, the light we measure contains contributions from both the planet and the star. If the planet truly has a water-rich atmosphere and the star spot also contains water vapor, the signals combine. If the planet has no atmosphere at all, but transits a water-laden star spot, the resulting spectrum can mimic an atmosphere perfectly. Untangling these overlapping signals requires observations across multiple wavelengths, comparing how the signal shifts under different conditions. Some wavelengths are sensitive to temperature, which differs between star and planet. Others respond to pressure. By combining this information, scientists can, in principle, separate the stellar contribution from the planetary one. But in the case of GJ486b, the available data fell short. The near-infrared spectrograph, or NIRSpec, measured wavelengths from roughly 1 to 5 microns, excellent for detecting water vapor, but not enough to distinguish the origin of the signal. That's why additional observations with the NIRS instrument are so crucial. NIRS extends down to 0.6 microns, the range where the two scenarios diverge more clearly. Star spots themselves move. GJ486 rotates roughly once every few weeks, carrying its spots across the stellar surface. The two transit observations of GJ486b were months apart, meaning any individual spot would have rotated many times. If a single star spot were responsible for the water signal, the signature should have changed between the two observations. Yet it remained consistent. This could mean the water resides in the planet's atmosphere, unaffected by stellar rotation. Or it could mean the star is so heavily spotted that the planet always crosses regions containing water vapor, no matter which spots it transits. Understanding star spots isn't an academic exercise. It's fundamental to interpreting every observation of every planet orbiting a red dwarf. Red dwarfs are notoriously harsh. The same ultraviolet light that nurtures life on Earth becomes a weapon around these stars. Ultraviolet photons carry enough energy to break molecular bonds. X-rays are even more destructive, ionizing atoms and stripping electrons. When this high-energy radiation hits a planetary atmosphere, chaos ensues. Water molecules are split into hydrogen and oxygen. Oxygen can combine with nitrogen to form nitrogen oxides, while the light hydrogen escapes into space. Over millions of years, entire atmospheres can vanish. Young red dwarfs are especially violent. In their first billion years, they erupt with near-constant stellar flares, massive explosions releasing as much energy as 1 billion atomic bombs. During these flares, X-ray and ultraviolet output can spike by factors of 10 to 100 for minutes or hours. A planet in close orbit experiences bombardment unlike anything Earth has ever known. Even the Sun's most extreme flares pale in comparison. Radiation doesn't just strip gas from the atmosphere, it can sterilize the surface entirely, breaking down organic molecules and rendering the planet uninhabitable. Scientists estimate that if Earth were placed in GJ486b's orbit, its atmosphere would be gone in less than 100 million years. The stellar wind, a continuous stream of charged particles, would blow away gases like a cosmic vacuum. Earth is protected by its magnetic field, which deflects these charged particles. But even strong planetary magnetism can only do so much. Around red dwarfs, the effect is magnified. The wind is stronger, the planet is closer, and only the largest worlds with the most powerful magnetic fields can hope to resist. G486b, though 3 times the mass of Earth, likely lacks a strong magnetic field. Rocky planets generate magnetism through a convecting liquid iron core. Earth's core still flows, creating our protective magnetic shield. Mars cooled and lost its field billions of years ago. Venus never developed a strong one at all. For a planet to maintain a magnetic field, it must retain enough internal heat to keep molten metal flowing. Larger planets can hold that heat longer, but even so, GJ486b's protective shield, if it exists, is likely weak. GJ486b, weighing 3 times as much as Earth, might harbor a molten core and an active magnetic field. Or it could be geologically dead, its interior frozen solid. Scientists do not yet know. Without a magnetic field, the planet is exposed, defenseless against the relentless stellar wind. With one, it gains a fighting chance. Yet even a magnetic shield cannot fully prevent atmospheric erosion over billions of years. That is why detecting any atmosphere here would be extraordinary. the star has had eons to strip it away. The planet orbits close enough that escape velocity is low, making the loss of gas easier. Every calculation suggests this world should be airless, yet the telescope has detected water vapor. How could it survive? The only plausible explanation points to volcanism. If GJ486b is still geologically active, volcanic eruptions could inject water vapor into the atmosphere faster than the star tears it away. On Earth, volcanoes release steam from underground reservoirs. On GJ486b, volcanoes might perform the same feat, but on a brutal, unrelenting scale, creating a temporary atmosphere that is constantly destroyed and replenished. The planet exists in a fragile equilibrium, a thin shell of air maintained by the endless cycle of creation and destruction. Imagine a planet bleeding steam from countless wounds. Volcanoes erupt across its surface, blasting superheated water vapor into the air. The star's radiation immediately begins to break down the molecules, letting hydrogen escape to space. Before the atmosphere can vanish completely, another eruption restores it. This is a brutal balance, the only way water vapor could persist under 800 degrees temperatures and relentless stellar radiation. Volcanic activity requires heat, and heat requires energy. Rocky planets inherit primordial heat from their formation, when countless impacts and gravitational compression heated the interior to thousands of degrees. They also generate heat through radioactive decay. Elements like uranium, thorium, and potassium release energy slowly over billions of years. A planet 3 times Earth's mass would contain proportionally more radioactive material, generating more internal heat. That heat must escape, flowing outward through the mantle, sometimes breaking through the surface as volcanism. Earth today hosts roughly 50 to 70 active volcanoes erupting at any moment, releasing water vapor, carbon dioxide, sulfur dioxide, and other gases. Over geological time, these eruptions helped build our atmosphere and oceans. On GJ486b, the process could operate in reverse. The atmosphere forms and is destroyed in a continuous cycle. On Earth, gas accumulated over millions of years because little was actively removing it. On this exoplanet, the star strips it away relentlessly. To maintain even a thin atmosphere, volcanism must be far more intense. Scientists can estimate the required volcanic activity by calculating atmospheric loss rates. The star's ultraviolet radiation and stellar wind sweep away gases at a speed determined by radiation intensity and the planet's gravity. Stronger gravity helps retain an atmosphere. Weaker gravity allows it to escape more easily. For GJ486b, the balance is delicate. The planet's mass gives it some advantage, but the close orbit and extreme stellar activity create a hostile environment where gas survival is a constant struggle. Gravity on GJ486b is roughly 3 times that of Earth, which helps hold on to an atmosphere, but the stellar radiation it receives is far more intense than anything Earth experiences. Balancing these forces suggests the planet would need volcanic activity at least 10 times greater than Earth's just to maintain a steady-state water vapor atmosphere. Could that happen? Perhaps. Io, Jupiter's volcanic moon, is the most geologically active body in our solar system, with hundreds of volcanoes constantly reshaping its surface under the influence of Jupiter's tidal forces. If GJ486b experiences similar or greater geological activity, driven by leftover primordial heat and radioactive decay, it could, in theory, supply enough volcanic gas to offset the relentless atmospheric loss. But there's no way to confirm this without direct observations of its surface, which remain far beyond current technology. The water itself would originate deep within the planet. During planetary formation, as dust and gas coalesced around young stars, water became trapped in mineral crystals, frozen as ice in cooler regions, or dissolved in molten rock. Over time, heat releases this water through volcanic eruptions. On Earth, the mantle alone holds more water than all our oceans combined. GJ486b's interior could similarly harbor immense reservoirs, feeding volcanic steam for billions of years. But even if volcanism is supplying water vapor, that does not guarantee a stable, Earth-like atmosphere. The reality would be a fragile veil of steam constantly replenished and destroyed. Atmospheric pressure might be just a fraction of Earth's, the air extending only a few miles above the scorching surface. Standing there, if survival were possible, you would barely notice it, a shimmering haze hovering over red-hot rocks. Whether this volcanic steam factory scenario is real hinges entirely on whether the water vapor is truly on the planet. and that remains uncertain. If it is, GJ486b could host something our solar system has never seen, an atmosphere made purely of steam. No nitrogen, no oxygen, no carbon dioxide, just water vapor encircling a rocky world at 800 degrees. Earth's atmosphere is 78% nitrogen, 21% oxygen, and roughly 1% water vapor. Mars has carbon dioxide. Venus has carbon dioxide and sulfuric acid clouds. Gas giants are hydrogen and helium with traces of methane and ammonia. But a planet cloaked in pure water vapor is unprecedented. Kevin Stevenson of Johns Hopkins University emphasizes that no analog exists in our own solar system. Scientists have no reference point, no template. They must build entirely new models from scratch, blending physics and chemistry in ways never tested. Temperature determines how water molecules interact. Pressure dictates how thick the atmosphere can become. Stellar radiation governs how long it can survive. On Earth, water exists in solid, liquid, and gaseous forms. On GJ486b, surface temperatures are far too high for ice or liquid. Everything becomes vapor. This superheated steam interacts with the rocky surface in unfamiliar ways. Water vapor can chemically alter minerals, slowly breaking down rocks over geological time. On Earth, similar reactions occur in volcanic fumaroles and hot springs. On this planet, such processes could span the entire dayside. Atmospheric chemistry would be extreme. Ultraviolet light from the star continuously splits water molecules into hydrogen and oxygen. Hydrogen escapes into space. Oxygen lingers, reacting with surface rocks and oxidizing metals like iron. The atmosphere would constantly lose hydrogen faster than oxygen, creating a chemical imbalance. Maintaining it would require volcanic eruptions to supply water vapor in the right hydrogen to oxygen ratio faster than the star disrupts it. If enough atmosphere exists, temperature gradients could drive extraordinary weather. The dayside, searing at 800 degrees, would generate rising columns of superheated steam. The night side, potentially hundreds of degrees cooler, would produce descending flows of condensing vapor. Winds could roar at supersonic speeds, possibly exceeding 1,000 miles per hour, transferring heat from day to night while generating turbulence, storms, and atmospheric dynamics unlike anything Earth meteorologists have ever studied. The atmosphere's thickness remains unknown. It could create surface pressures rivaling Venus, or it could be so thin as to barely register, a mere whisper of air. Transmission spectroscopy reveals only water vapor's presence, not its quantity or pressure. Future observations may uncover more by mapping how the atmosphere redistributes heat across the planet. But before scientists can probe these alien properties, they first must confirm the atmosphere exists at all. And to do that, they must wrest a signal from a star that outshines the planet by billions of times. Stars are blinding. This is the fundamental challenge of studying exoplanets. Stars outshine their planets by billions of times. Observing a planet next to its star is like trying to spot a firefly next to a blinding searchlight. For decades, this glare made direct detection impossible, forcing scientists to rely on indirect methods, measuring the subtle ways planets tug on or dim their stars. Then, coronagraphs were invented, instruments designed to block starlight while letting planetary light through. The concept sounds simple, but in practice it is extraordinarily delicate. Coronagraphs use precisely shaped masks or carefully angled mirrors to cancel out starlight through destructive interference while preserving light from nearby planets. The James Webb Space Telescope carries several coronagraph designs, each optimized for specific scenarios. For a transiting planet like GJ486b, the telescope doesn't need one because the planet passes directly in front of the star. But for direct imaging of other exoplanets, especially Earth-like worlds orbiting Sun-like stars, coronagraphs are essential. These masks are engineering marvels, shaped with intricate concentric circles or spirals that manipulate light waves so that the star's glare diminishes by factors of thousands or millions, while nearby planetary light passes through relatively untouched. The system is so sensitive that even tiny imperfections in the telescope's mirrors or minuscule vibrations can create artifacts that mimic planets. Engineers spend years testing, calibrating, and observing reference stars to distinguish real signals from false ones. JWST's coronagraphs operate in infrared light, invisible to human eyes but ideal for studying planets. Rocky worlds emit most of their light in infrared due to surface heat, while gas giants glow in infrared from residual formation heat. Observing in this spectrum increases the planet-to-star brightness ratio dramatically, reducing the gap from billions to millions or thousands. For GJ486b, spatial separation wasn't necessary. During transit, the planet casts a tiny silhouette against the star, blocking a fraction of starlight. JWST measures this dip and analyzes the filtered light to search for atmospheric fingerprints. No coronagraph is required, but for planets that don't transit, coronagraphs remain indispensable. The next challenge is selecting the right instrument. JWST has two that can study planetary atmospheres, each providing complementary information. Near-infrared spectrograph, or NIRSpec, captured the water vapor signal from GJ486b. Near-infrared imager and slitless spectrograph, or NIRIS, could help determine whether that water originates from the planet or the star. NIRSpec observes from 0.6 to 5.3 microns, prime territory for molecular absorption. Water vapor absorbs around 1.4 and 2.7 microns, carbon dioxide near 4.3 microns, and methane around 2.3 and 3.3 microns. NIRSpec spreads these wavelengths into detailed spectra, revealing which molecules are present and in what concentrations. High-resolution mode provides exquisite spectral detail, but the instrument struggles below 1 micron, the very range where planetary atmospheres and stellar star spots diverge. At these short wavelengths, models predict planetary water vapor produces one type of spectral signature, while star-spot water vapor produces another. NIRSpec cannot fully resolve this difference. This is where NIRIS comes in. It covers 0.6 to 2.8 microns, with excellent sensitivity below 1 micron, and employs single-object slitless spectroscopy, ideal for bright red dwarf stars. NIRIS can observe an entire transit from start to finish, producing time-resolved spectra. If the water vapor originates from GJ486b, the absorption remains consistent throughout the transit. The planet carries its atmosphere along. If it comes from star spots, the signal varies as the planet crosses regions of different temperatures and spot coverage. The uneven distribution of spots across the stellar surface could produce a time-variable water vapor signature. Theoretical. Models suggest planetary water vapor creates a rising spectrum toward shorter wavelengths, while stellar water vapor produces a falling spectrum due to temperature differences. Planetary atmospheres at 800 degrees behave very differently from stellar photospheres at 6,000 degrees with embedded 4,000 degrees spots. NIRIS has the capability to observe this divergence and finally determine whether the water is planetary or stellar. But the observations have not yet been completed. Telescope time is precious and competitive. Hundreds of proposals vie for limited hours. Some are approved immediately. Others wait years. GJ486b's NIRIS observations were approved, but the exact timing remains uncertain. Until that data arrives, the mystery endures. Meanwhile, the story grew more complicated. On August 24, 2024, a new paper landed like a bomb in the debate over GJ486b. Its title was blunt: No Thick Atmosphere on the Terrestrial Exoplanet GJ486b. The study presented results from 2 additional telescope observations using secondary eclipse spectroscopy. Rather than watching the planet transit in front of the star, these observations measured what happens when the planet passes behind the star. The August 2024 paper challenged everything the earlier transmission spectroscopy seemed to suggest. Secondary eclipse spectroscopy reveals a very different story than transits. Instead of watching the planet pass in front of its star, scientists observe what happens when the planet slips behind the star. During this brief eclipse, the system's total brightness drops ever so slightly because the planet's own thermal emission is hidden from view. By measuring how that brightness changes across different wavelengths, researchers can determine the dayside temperature of the planet and look for emission features from its atmosphere. If GJ486b possessed a thick atmosphere, it would carry heat from the scorching dayside to the cooler nightside, and infrared spectral features would betray the presence of molecules glowing in the heat. The new observations showed none of this. The dayside temperature measured at 865 degrees F, plus or minus 14 degrees, is precise enough to leave little doubt. More importantly, this temperature tells scientists something fundamental about heat transport. By comparing the observed temperature to the theoretical maximum for a bare, airless rock, they can see how efficiently the planet moves heat around. A rock with no atmosphere absorbs starlight on the dayside, and radiates it as infrared heat without redistributing it. For GJ486b, the measured temperature is 97% of that maximum. This near-perfect match suggests the planet barely redistributes heat at all. A thick atmosphere would have carried warmth to the night side, lowering the day-side temperature well below this level. Instead, the planet behaves like bare rock. The paper concludes that GJ486b either has no atmosphere, or perhaps an ultra-thin one, less than 1% water, vapor, or less than 1 part per million of carbon dioxide. How? Does this reconcile with the water vapor hinted at in transmission spectroscopy? The answer may lie in what each technique actually probes. Transmission spectroscopy samples starlight, filtering through the very uppermost layers of a planet's atmosphere, tenuous, high-altitude gas. Secondary eclipse spectroscopy, by contrast, measures thermal emission from the entire day side, sampling much deeper layers. It's possible a thin, wispy layer of water exists high in the atmosphere, detectable by transmission spectroscopy, but not enough to redistribute heat or constitute a substantial atmosphere. Alternatively, the transmission spectroscopy signal may have been contaminated by water vapor in star spots rather than originating from the planet itself. The secondary eclipse data support this interpretation. If a dense water vapor atmosphere had been present, it would have transported heat, lowering the dayside temperature, yet no such effect is observed. The scientific process unfolds precisely as it should. One team reports a detection, another tests it with a different method, and the results disagree. Now, researchers must determine which observation is more accurate, or whether both are correct, but measuring different aspects of the system. The debate continues, but the odds increasingly favor the star spot explanation. But what does no thick atmosphere actually mean? Airless does not imply a perfect vacuum. Mercury, the most obviously airless planet in our solar system, maintains a faint exosphere of atoms kicked off its surface by solar wind impacts. The Moon has something similar. These atmospheres are millions of times thinner than Earth's, too tenuous to breathe or hear through, effectively negligible for most purposes, but detectable by sensitive instruments. When scientists describe GJ486b as airless, this is the sense they mean: an atmosphere so thin it barely matters, more a ghostly veil than a true envelope of gas. For comparison, Earth's atmospheric pressure at sea level is about 14.7 pounds per square inch. On GJ486b, any existing air would be far, far less than that. Atmospheric pressure comes from the weight of all the air above pressing down. Climb a mountain, and the pressure drops because there is less air overhead. Travel to space, and it falls nearly to zero. The boundary between atmosphere and space is fuzzy, but most definitions place it around 60 miles above a planet's surface. Beyond that, the air is so thin that spacecraft barely experience drag. Venus offers a stark contrast. Its surface pressure is 90 times that of Earth. Standing there, the weight of the air alone would feel like being 3,000 feet underwater, crushing the body long before the heat could. Mars lies somewhere between these extremes. Its surface pressure is only about 0.6% of Earth's, too thin to breathe, yet thick enough to produce weather, dust storms, and clouds. These are substantial atmospheres in the sense that they actively shape a planet's climate and surface. GJ486b might host something far thinner. Imagine an atmospheric pressure 1/10 that of Mars, or 100th, even 1,000th. At some point, calling it an atmosphere becomes almost misleading. It would resemble a faint haze of molecules, occasionally colliding with the surface before escaping to space. Such a tenuous veil would do nothing to transport heat, form weather, or shield the surface from stellar radiation. It would barely interact with starlight. Yet, if those molecules congregate at high altitudes, transmission spectroscopy might still detect them. When the August 2024 paper refers to no thick atmosphere, the wording is deliberate. It rules out Earth-like or Venus-like envelopes of air, but leaves room for an ultra-thin layer. The abstract states, the results are consistent with an airless body with a slight non-zero albedo, or a thin atmosphere with less than 1% water vapor. That phrasing, less than 1%, is crucial. For context, Earth's atmosphere contains about 0.4% water vapor on average. Less than 1% could still mean a measurable amount of water on GJ486b, just not enough to influence heat transport or produce significant secondary eclipse signals. Understanding these nuances matters because the definition of an atmosphere determines whether GJ486b represents a historic discovery or a false alarm. Even a whisper of genuine atmosphere, far thinner than Mars's, would mark the first rocky exoplanet with confirmed atmospheric gas, a milestone for understanding planetary formation and evolution. If, however, the planet is truly airless and the apparent water signal arises from star spots, scientists must continue their search for the first rocky exoplanet atmosphere. This semantic debate underscores a deeper truth in exoplanet science. Red dwarf stars host a vast graveyard of dead atmospheres. Billions of rocky worlds orbit these cool suns across the galaxy, and most likely began with air. Gas left over from formation would have enveloped these planets, creating primordial atmospheres rich in hydrogen, helium, water vapor, and other volatiles. Then the stars awoke. Young red dwarfs, especially in their first billion years, unleash radiation storms that dwarf even the sun's wildest tantrums. Ultraviolet light, X-rays, and flares can increase stellar output by factors of 10 or more, stripping atmospheres layer by layer until only bare rock remains. This is the M-dwarf planet problem. M-dwarfs are the universe's most common stars, making up roughly 70% of all stars. Rocky planets around these stars are even more common. Estimates suggest billions of Earth-sized worlds orbit red dwarfs in our galaxy alone. But if these planets cannot retain their atmospheres, they cannot support life. Billions of potential worlds are reduced to sterile rocks. For decades, scientists debated the fate of these planets. Some argued that rocky planets orbiting M-dwarfs would be airless without exception. The radiation is too intense, the orbits too close, atmospheric escape inevitable. Others proposed that some planets might cling to their air through protective mechanisms. Strong magnetic fields deflecting stellar wind, higher planetary mass generating stronger gravity, or continuous volcanic outgassing, replenishing an atmosphere faster than it is destroyed. The debate has remained largely theoretical because, until recently, no one could definitively detect or rule out atmospheres on rocky exoplanets orbiting red dwarfs. GJ486b was poised to change that. Its size gives it strong gravity, a natural ally in holding onto an atmosphere. Its star, billions of years past its violent youth, seemed to have calmed enough that any fragile air might survive. If a rocky planet around a red dwarf could retain an atmosphere, this one appeared to be the most likely candidate. When the initial detection of water vapor came through, hope surged. Perhaps atmospheres could endure after all. Perhaps billions of worlds across the galaxy remained habitable. But the August 2024 paper, asserting no thick atmosphere exists, pulled the tide of optimism back out to sea. Maybe atmospheres cannot survive around these stars. Perhaps the red dwarf graveyard is real, littered with airless rocks stripped bare by relentless radiation. The stakes go beyond habitability. The survival of an atmosphere dictates where scientists should look for life. Most searches for biosignatures focus on atmospheric gases produced by life, like oxygen or methane. If rocky planets around red dwarfs cannot maintain atmospheres, the hunt for life must shift toward planets orbiting sun-like stars instead. But these stars are far rarer than red dwarfs, shrinking the pool of potentially habitable worlds and extending the timeline for discovering life from decades into centuries. Planetary mass complicates the picture. Larger rocky planets hold onto their air more easily, their gravity resisting atmospheric escape. GJ486b, at 3 times Earth's mass, sits at the upper edge of rocky planet sizes. If even this massive world struggles to keep an atmosphere, Earth-sized planets stand little chance. Conversely, if GJ486b does harbour an atmosphere despite the odds, it suggests that smaller worlds might hold on to theirs under the right conditions. The answer determines which planets warrant study and which can be ignored. For now, the question remains agonizingly unresolved. Some observations hint at water vapor, others deny the presence of a thick atmosphere. Until someone can definitively confirm or rule out atmospheric gas on this or similar worlds, the M-dwarf planet problem remains open. But we have another world for comparison: Venus. GJ486b and Venus are twins across cosmic distance. Both are rocky, both endure surface temperatures around 800 degrees Fahrenheit. Both orbit closer to their stars than Earth does. Yet Venus boasts a crushing atmosphere of carbon dioxide, while GJ486b may be bare rock. Understanding why these two similar worlds diverged could reveal fundamental truths about planetary evolution. Venus's atmosphere weighs 90 times as much as Earth's, crushing the surface as if standing 3,000 feet underwater. It is 96% carbon dioxide, with clouds of sulfuric acid drifting 30 meters above the surface. These clouds reflect much of the sunlight, giving Venus a high albedo, yet enough light penetrates to heat the ground. The thick carbon dioxide traps that heat through a runaway greenhouse effect, maintaining hellish temperatures day and night. How did Venus arrive at this fate? The planet likely began with oceans similar to early Earth, but Venus's closer orbit bathed it in nearly twice the sunlight. That extra energy evaporated oceans into the atmosphere. Water vapor, a potent greenhouse gas, trapped heat, further accelerating evaporation. The cycle intensified until all the water existed as vapor. Ultraviolet radiation split the water molecules. Hydrogen escaped to space. Oxygen reacted with surface rock. Oceans vanished, replaced by carbon dioxide emitted from volcanoes, which now accumulated in the atmosphere with no oceans to absorb it. GJ 486b could have followed a similar trajectory. It may have begun with oceans of water, only to have them boil away under its star's intense radiation. Water vapor would have built up in the atmosphere, only to be split apart by ultraviolet light, even more efficiently than Venus experienced from the sun. The stage was set for a world stripped bare, leaving behind the tantalizing question, does any atmosphere remain, or has the red dwarf graveyard claimed yet another rocky planet? Hydrogen escaped, oxygen escaped or reacted with surface rocks. The water vanished, perhaps within a few 100 million years. Unlike Venus, which later built up a thick carbon dioxide atmosphere, GJ 486b may never have experienced substantial volcanic outgassing. Or if it did, the planet's star might have stripped that gas away as efficiently as it did water. The result, a world essentially without air. The comparison with Venus, however, is revealing. Venus retains its dense atmosphere partly because it sits far enough from the sun that stellar wind cannot strip it away efficiently. Venus may lack a strong magnetic field, but its thick air protects itself. The upper atmosphere absorbs ultraviolet light and deflects solar particles, shielding the lower layers. GJ 486b, in contrast, hugs its red dwarf closely. Stellar wind here is far more intense. Even if volcanic activity attempted to build a protective layer, the planet's star might remove gas faster than it can be replenished. Temperature differences tell a similar story. Venus is hot because its greenhouse gases trap heat. Its surface is insulated from the cold of space. Remove that atmosphere, and Venus would be far cooler. GJ 486b is hot because of proximity to its star. Strip away any thin air, and the surface temperature hardly changes. The planet's heat comes from external radiation, not internal atmospheric insulation. Venus trapped its own heat. This world cannot. This comparison highlights how small differences in orbital distance, stellar type, and planetary properties can produce wildly different outcomes. Venus ended up with too much atmosphere, a suffocating envelope of carbon dioxide. GJ 486b may have ended up with too little, or none at all. Both worlds are hellish, but in very different ways. Understanding this distinction frames an essential question. Would discovering any atmosphere on GJ 486b count as a first? Scientists have already studied atmospheres on hundreds of exoplanets. Gas giants like Jupiter reveal clear spectral signatures. Hot Jupiters, gas giants orbiting closely to their stars, have atmospheres probed in extraordinary detail. Water vapor, methane, carbon monoxide, even atomic metals have been detected. These techniques excel for large planets with thick envelopes. Rocky planets are another story. Small, thin, if they have any atmosphere at all. Signals are subtle, fleeting, easily drowned out by stellar interference or instrumental noise. Until GJ 486b, no rocky exoplanet beyond our solar system had a confirmed atmosphere. Detecting one would shatter a barrier standing since the first exoplanet was confirmed in 1995. Thousands of planets have been found since, thousands of gas giants studied, yet zero Earth-like or Venus-like rocky worlds with detectable air. The technical challenge is immense. Rocky planets are small, 1 to 3 times Earth's size. Their atmospheres are thin, spectral features faint, and easily confused with stellar contamination. Proving GJ 486b has an atmosphere would validate decades of instrument development, analysis techniques, and observation strategies. Transmission spectroscopy, secondary eclipses, and other methods would be confirmed capable of detecting the faintest signals. That validation would justify building more powerful telescopes, designed specifically to probe rocky planet atmospheres. Funding would flow, research programs would accelerate, and the search for habitable worlds could leap forward by decades. But the stakes cut both ways. If GJ486b turns out to be truly airless, it implies rocky planet atmospheres are harder to detect than pessimists feared. Current instruments may not yet have the sensitivity needed. Future telescopes would require larger mirrors, finer instruments, and new methods to probe these elusive worlds. The timeline for characterizing Earth-like planets and ultimately searching for life could stretch from years into decades. Discovery would belong to future generations, leaving the present to wait, instruments trained, and telescopes poised for the day when the first rocky exoplanet atmosphere is finally revealed. The historic significance of GJ486b hinges entirely on ambiguous data. If transmission spectroscopy truly detected planetary water vapor, and the secondary eclipse observations simply missed a thin atmosphere, then GJ486b earns its place in the history books. But if transmission spectroscopy only picked up stellar water vapor from star spots, and the secondary eclipse observations are correct in showing no planetary atmosphere, the search continues. The line between a first confirmed rocky exoplanet atmosphere and another false alarm rests on observations that have yet to be completed. Scientists are careful not to claim victory prematurely. As Sarah Moran put it, we see a signal, almost certainly water, but we cannot yet tell if it belongs to the planet's atmosphere. That uncertainty is honest and necessary. Rushing to declare a discovery that later proves false would damage scientific credibility. It is far better to wait for definitive proof than to risk a premature announcement. The wait continues. Additional observations are planned. New analysis methods are being developed. Other rocky exoplanets around red dwarfs are being studied using similar techniques. One way or another, the question will be answered. Either GJ486b has an atmosphere, or it does not. Either it becomes the first, or the search presses on. Either way, the answer matters far beyond a single planet 26 light-years away. If GJ486b can hold even the thinnest atmosphere under 800-degree temperatures and relentless stellar radiation, it would reveal something profound about rocky worlds. This planet orbits well inside the habitable zone, tidally locked with one side baking, the other freezing, every factor working against atmospheric survival. Yet transmission spectroscopy detected water vapor. Even if the atmosphere is thin, even if it is constantly replenished by volcanic outgassing and stripped by stellar wind, its mere existence proves that rocky planets can retain air in hostile conditions. Now imagine a similar planet orbiting a red dwarf farther from its star. Cooler surfaces, less intense radiation, more time for water vapor to persist before breaking down. Such a planet could maintain a stable atmosphere without constant replenishment, nurturing oceans, clouds, weather, a functioning water cycle, the very ingredients for life. If GJ486b, the most extreme case, manages to keep even a thin atmosphere, these gentler worlds almost certainly can as well. The billions of rocky planets orbiting in red dwarf habitable zones across the galaxy remain compelling targets in the search for life. But if GJ486b is truly airless, the consequences are stark. If even this massive high-gravity planet cannot hold onto atmospheric gas, what hope remains for smaller Earth-sized worlds? Perhaps none. Rocky planets around red dwarfs may universally lose their atmospheres during their star's violent youth. The billions of potentially habitable worlds may instead be barren, sterile rocks. Life-seeking efforts would then need to focus on planets orbiting sun-like stars, which are rarer, dimmer, and harder to study. There is a middle scenario. Perhaps only the largest rocky planets, like GJ486b at 3 times Earth's mass, can cling to air around red dwarfs. If so, millions of super-Earths might still maintain atmospheres, preserving the possibility of life in certain corners of the galaxy. Optimism would be tempered, but the cosmos would not be empty. The question of GJ486b's atmosphere, then, is not just a matter of one planet. It is a litmus test for the potential habitability of billions of worlds scattered among the stars. Finding life beyond Earth may be harder than hoped, but it is far from impossible. GJ486b may force us to rethink the very concept of the habitable zone. Traditionally, scientists define it by the distance from a star where liquid water could exist on a planet's surface. But if planets orbiting red dwarfs cannot retain atmospheres, the inner edge of the habitable zone is determined not only by temperature, but also by the survival of air itself. A planet might be cool enough for liquid water yet entirely airless, rendering it uninhabitable despite falling within the traditional habitable zone. The true habitable zone could be narrower than previously imagined. Atmospheric stability also dictates the potential for life. Even if GJ486b possesses a thin atmosphere, constantly replenished by volcanic outgassing and stripped by stellar wind, such a dynamic environment may be too hostile for life. Life, as we understand it, requires stability, consistent conditions over millions of years for evolution to take hold. Yet life is adaptable. On Earth, extremophiles thrive in volcanic vents, acidic hot springs, and deep ocean trenches. Perhaps alien extremophiles could survive on worlds with transient atmospheres, clinging to fleeting pockets of habitability. Ultimately, the answer depends on what we discover on GJ486b and similar worlds. Each rocky planet studied adds critical data. Each confirmed or ruled out atmosphere helps define the limits of planetary survival. Patterns will emerge over time, guiding where to focus the search for life and where to avoid wasted effort. It is vital, however, to clarify a common misconception. Detecting water vapor does not equate to discovering life. This distinction cannot be overstated because the public often conflates the two. Water is essential for life as we know it. Every organism on Earth requires it, but water alone is not life. Water exists throughout the cosmos without biology. Jupiter has it, Saturn has it, comets are largely ice, and even the moon hides water ice in shadowed craters. None of these places host life. Water is necessary, but nowhere near sufficient. Biosignatures are far more specific. They are combinations of gases produced by life that cannot be easily explained by geology or atmospheric chemistry alone. On Earth, oxygen serves as a prime example. Our atmosphere contains 21% oxygen because photosynthetic organisms constantly produce it. Without life, geological processes would remove oxygen within a few million years through reactions with rocks and volcanic gases. Yet even oxygen alone is not conclusive. Planets can generate oxygen abiotically, such as through the ultraviolet-driven splitting of water vapor. The most compelling, biosignatures arise from chemical combinations that are unstable. Without biological replenishment, oxygen and methane together, or methane and nitrous oxide, their coexistence signals active life because geology alone cannot maintain them over time. Detection increases confidence. A single gas may provide 10% certainty, but the right combination can boost confidence to 90%. Absolute proof, however, requires observing life directly. GJ486b's water vapor, even if confirmed to originate from the planet, has zero biosignature value. It could be explained entirely by volcanic outgassing, requires no life, and provides no evidence for habitability. Its surface is 800 degrees Fahrenheit. If life exists there, the water vapor detection tells us nothing about it. The water is geologically fascinating, atmospherically informative, but biologically irrelevant. This distinction matters because media coverage often sensationalizes exoplanet discoveries. Headlines proclaim, "Water found on alien world, aliens imminent," creating misconceptions. The reality is far more measured. Scientists have detected hints of water vapor that may come from the planet, or from star spots on the host star. Even if it originates from the planet, it merely suggests geological activity, not life. Maintaining realistic expectations preserves public trust in science. False positives further complicate the story. In the history of exoplanet research, potential biosignature detections have sometimes been traced to instrumental errors, stellar contamination, or misinterpreted data. Each false alarm erodes public confidence, making genuine discoveries harder to communicate. In science, as in life, crying wolf too often diminishes credibility. Overclaiming biosignatures risks the same, highlighting the importance of patience, precision, and restraint in interpreting data. It is better to be cautious, to distinguish clearly between what has been found and what remains unknown. GJ486b serves as a masterclass in studying rocky exoplanet atmospheres, assuming it has one. The lessons learned here will guide future observations of truly Earth-like worlds in habitable zones, where biosignatures might actually exist. Consider this planet a practice target, a dry run, a rehearsal for the moment when the James Webb Space Telescope or other future instruments examine a world capable of supporting life. The techniques refined on GJ486b, separating planetary signals from stellar contamination, choosing optimal wavelengths, testing analysis methods, will be ready when the real stage arrives. What comes next remains uncertain. The story of GJ486b is far from complete. Additional observations using Webb's NIRSpec instrument could definitively determine whether the detected water vapor originates from the planet or the star. These observations are scheduled, likely within the next year or two, and when the data arrives, scientists will scrutinize it and publish their findings. If NIRSpec reveals that the water is stellar, the planet is likely airless, and the hunt for the first rocky exoplanet atmosphere continues. But if the water is planetary, even a thin atmosphere will mark a historic milestone. Beyond GJ486b, dozens of similar worlds await study. Hundreds of rocky exoplanets orbit red dwarf stars close enough for detailed atmospheric characterization. Some may even be better targets than GJ486b, stars that are calmer, or planets with orbits more favorably aligned. The telescope can observe only a fraction of these worlds during its mission, forcing scientists to make difficult choices about where to focus their precious observation time. The Nancy Grace Roman Space Telescope, slated for launch in 2026 or 2027, will join the search, complementing Webb with new capabilities, including direct imaging of planets rather than relying solely on transits. Together, Webb and Roman will provide richer, overlapping datasets, each capable of catching what the other might miss. Ground-based telescopes are advancing as well. The extremely large telescope under construction in Chile will feature a 39-meter primary mirror, capturing more light than any previous telescope and enabling atmospheric studies of rocky planets around nearby stars. Adaptive optics will counteract Earth's atmospheric turbulence, creating sharper images than ever before. The combination of space and ground-based observations promises to accelerate progress. Looking further ahead, proposals for even more ambitious missions exist. Telescopes specifically designed to study Earth-like planets, equipped with dozens of instruments optimized for biosignature detection. These projects will take decades and billions of dollars, and their fate depends in part on current observations. If Webb confirms atmospheres on multiple rocky exoplanets, funding agencies will be more inclined to support these next-generation missions. If rocky atmospheres remain elusive, priorities may shift elsewhere. The ultimate goal is to find life. Every step toward characterizing rocky exoplanet atmospheres brings us closer. GJ486b may lack life, or even a substantial atmosphere, but studying it refines the techniques needed to find habitable worlds. Each observation teaches something. Each ambiguous result points to better methods for the next attempt. Science progresses incrementally through painstaking work like this. In the coming years, perhaps sooner, scientists will know definitively whether GJ486b has an atmosphere. They will understand whether rocky planets around red dwarfs can survive the onslaught of stellar radiation. They will know where to focus the search for habitable worlds, and the answers will reshape our understanding of life's potential abundance in the galaxy. Humanity will learn whether neighbors await discovery, or whether we are alone among billions of sterile rocks orbiting distant red dwarfs, each planet either shrouded in steam or bare as a lunar surface. Across laboratories and universities, scientists wait for telescope time, analyze data and debate interpretations. The mystery persists, the ambiguity frustrates, but the search continues. Somewhere in the cosmos, perhaps on a world much like GJ486b but farther from its star and cooler, life may exist. Discovering it begins with understanding planets like this one, learning which can hold air and which cannot, and building the tools and knowledge to answer humanity's oldest question: are we alone? The answer, whatever it is waiting, flickering in the light that filters through distant, unseen atmospheres.